If you're giving a talk today, I recommend not staring straight into the light of the projector, because I can't see the screen or anything now. I've got all spots in front of my eyes. Very bad idea to do that. I can see it a little bit. So I realized coming here today that I saw the talks are 25 or 40 minutes. And I said, I didn't check. Do I have 25 or 40? What if I have 15 extra minutes? So what I did was I thought, well, I brought a bunch of sea chanties I could sing for the 15 extra minutes and fill up the time. And I thought, geez, maybe I could do the sea chanties instead of the presentation. You know, my students have heard the sea chanties. They know, oh well. So we'll go on with the presentation instead. All right. The reason for this project was I was teaching operating systems last spring, and I wanted to have my students do some assembly language, but I did not want to involve them. Well, so we want them to do some assembler, and this is useful when the students aren't studying assembly language, but they're doing a course on system architecture, operating systems, C, a course on compilers. They should be familiar with assembler and have some idea of how it's working. So I contemplated what they would have to do to actually run a native assembler. They have a diverse set of laptops, so this would be different on each one. I was going to be showing them things like, although the AMD 64 architecture uses 64-bit pointers, implementations are only required to handle 48-bit addresses. Therefore, conforming processes may only use addresses from this range here. And you know, teaching them the load options to get those right type of addresses. And then we were going to have to debug our programs, and we were going to be looking at something like this when we went to debug them. And this would be different for Mac, for Windows, for Linux, and I thought this doesn't look pretty. I searched around. I said someone must have done something that makes it easy to try out assembler without having to get into all these command line tools. I didn't find anything. So what I did was, I think we'll make the font a little bigger, huh? What I did was build something. And this is online assembly language interpreter. It's built with Python and Django. And we can do yes, thank you. Doesn't catch typo. This is something nice we could build in, but it's not there now. Oops. Move E8. I did EAT. It's the problem with doing this live. And this is EAB, huh? Okay. So in any case, oh man. EA. I swear this thing works. Well, I don't know what's up with it right now. Whenever you do this live, you hit something like this. It does work. Oh, I got EAB. It's EBX, right? There we go. All right. There we go. See, it does work, I swear. And we've loaded this. We can also step the code. We can clear memory. We can save the code. We've got some JavaScript running that can give us more information on what's going on here. This has come out fairly nicely. An interesting aspect of doing this was that for doing something like stepping code, we've got a problem of state. And basically what we do is we use the REST paradigm and we just pass the entirety of the state. I realized preparing this talk that what this structure really should have been called was the machine. So we're passing the entire state of the machine at any point during the running of the program back and forth. And because we've got things like the instruction pointer in the registers, we can tell where we are in execution at any particular point. in our design, we completely separated. So our front end that you looked at there, the front end is all Django and Python with JavaScript additions. The back end is completely separated. There's a single entry point into the interpreter. So here I'm running in IPython, and I can load the interpreter itself and pump in an assembly language instruction to move into 12 into EAX, and we get the right result. This is handy. We don't need to keep rebooting a web server to test code. It also means that as we go forward, we're working on making this an IPython or Jupyter kernel, so that we don't have to call the assembler function. We can simply put in assembly language code straight into the shell. And because of the design, this could be available as a microservice if someone, for some reason, wanted to send assembler code to a microservice. I don't know why anyone would want to do that, but it's a possibility. We're going to look at some of the implementation details next. There's the flat is better than nested principle in Python, and that's certainly true if you have a bad object-oriented design, that a flat design is much better. But a good object-oriented design can capture a lot of features of the domain you're working in. So this is a base class for tokens, because as we're interpreting, everything that we pull in that's typed in is going to be turned into a token. So underneath token, we then our instructions, our classes, and the instruction is called by calling all instructions have this single point that called F that actually executes the instruction code. So here we have some other subclasses from token. We have a location. We have, location is a type of operand, which is subclass from token. We have addresses and register addresses. So what this means is that the class hierarchy nicely reflects the domain. So this is just a sketch of the whole class hierarchy. It doesn't have everything. But basically, you get a description of the syntax of assembly language right in your class hierarchy, which is very nice, makes it very easy to know what you've got at hand if you're debugging the interpreter. The instruction class makes it very easy. Our jump table, we just install one of the, so underneath instructions, each specific instruction, we have 3 types under that: control flow, data movement, and arithmetic. And each of those, we have a type for the specific instruction. And we just instantiate that, and then we're going to find what instruction we have by looking up JNZ or JG or JGE in the table, and then we're going to call the F method of that object. So very simple, very straightforward to make the jump table and know what to do as we interpret an instruction. Assembly language, of course, is a bunch of go-tos, right? This is how you do control flow, and this is problematic, but in Python what we do is we raise a jump exception whenever we need to go somewhere, and the jump exception is associated with a place in the code to jump to. So there's going to be, you see, we're raising jump with a target name. So this is how we find where we're going to jump to in the code. Another nice feature of Python we were able to take advantage of for almost all of our arithmetic operators, they wind up just calling these 2 functions and then passing in an operator. So we use the functional operators that Python provides us. So add is just going to be, it's just going to call to-op arithmetic and pass in the plus functor, right? And minus, subtraction is going to call to-op arithmetic and pass in the subtraction functor. So this was very nice. We got to reduce a whole ton of code to just 2 functions. So we are using Django at present, and here he is. For people who don't know, the Django framework was named after Django Reinhardt, a famous jazz guitarist, and this is him here. So right now we use it mostly for templates. It was a framework we were already familiar with when we started building this. So we rolled ahead, even though we're not using the database much. However, it's given that we're built on Django already, it would be relatively easy for us to implement student logins so that students could actually be saving their source code associated with their login name. So we have this future plan. We don't know what else we might use the database capabilities for, but we're open to ideas. So we decorate the front end with some JavaScript. We do binary translation. We have error messages, which apparently are broken at the moment because what we saw should have been bringing up JavaScript errors and not throwing exceptions. But we also can, we use the new HTML5 store and load mechanisms through JavaScript so that you can store your current session in your browser and then reload it. And because of the design, because we have the user interface completely separated from the actual assembler, we don't have any tie-ins. The JavaScript doesn't know anything about Python, the Python interpreter, and the interpreter doesn't have any clue about the JavaScript code, and they don't need to. I'm running ahead here. I think we're going to finish early, but so how has this worked out? We found Python is a great language for building a little language. We're not trying to implement all of x86 assembler. For instance, at the moment, you can't overflow or register. We're gonna, because Python, we're using Python ints as the underlying storage, and of course, you can't overflow a Python integer. So there's no inherent overflowing. We're gonna actually have to build that in so that it's more realistic. But it's just not necessary for us to have a complete assembler for the tool to be useful, because it's intended as an educational tool, not as a way to build assembly language programs that you're then going to assemble. One thing that occurred to me after working on this was that there is, in fact, low-hanging fruit like this. This seemed like something obvious that should have been out there, and I looked for it and didn't find it. So does it actually, is it actually, was I mistaken that it was not needed? Well, I used it in my class, but this semester, as I understand it, it's in use by about 300 students at NYU who aren't my students. So this is good. It's turning out to be quite useful. And the project is open source. This web page is, I'm presenting here from a web page. The web page is up online, and you can find the GitHub repository here. If you, we called it Emu86, and there's our little emu up at the top of the page. So if you just Google for that and Callahan, probably just Emu86, you'll find this. We'd love to have more contributors. So we need to build the data section. We need to build system calls. Our stepping is interesting because we're throwing the whole machine state back and forth. And right now, the way it's built, we actually do a typical lexical analysis phase, and then we actually do the execution of the tokenized code. So the lexical analysis phase creates these Python objects, and then the execution is run on the Python objects. So we actually need to build in something to keep the actual line written of source code so that when we're stepping, we can show that. What we do right now is we uninterpret the tokens, since we know the name of each token and the name of the operands. But this may not be exactly what you wrote, because jump not equal and jump not zero are the same instruction, for instance, and jump equal and jump zero. So we just have to guess. We just picked one of them. So you might have written the other, and when we show what line we're stepping through, it might not exactly match the one you chose. So we need better stepping as well. Ultimately, it would be lovely to be able to highlight the line of source code that they're on. Right now, we just have a little window down below that says, here's the line we're executing. Well, you're not going to need the 5-minute sign. I think I'm done. So, is there any questions? All right. Well, I'll have to go to the sea chanties, folks, if you're not going to ask anything. It's bad news. Yes. Oh, yeah, well, the first feedback we got was the bugs we had, right? Because one of the things was we had been using the software correctly. And immediately the students began using it incorrectly because they didn't know, like we did, how it's supposed to be used. So this was great. We immediately found a bunch of bugs that, and we're working on, we have an automated test suite, and it's pretty good. I don't know what just happened. We should have gotten on errors in the user interface with those mistakes I was just making. So I've got a little work to do when I get home to find out what just happened, that we're not getting on-screen errors instead of errors from Django itself. But otherwise, students seem to get it. They enjoyed it. I think it was certainly easier than trying to teach them the assembler and the loader and a disassembler to get them to do it with a real system. All right, yes? Yeah, an assembly language program often starts with a data section where you declare names for memory and so forth. So we don't have that right now. We do have labels to jump to, but we don't have named sections of memory. So we need to build that in. It should be pretty straightforward. It's the same kind of operation as a label, but we haven't built it yet. All right, well, thank you very much.